last time we started with the multiple server queue model, and that's a classic place to start, because that's actually a notoriously challenging model, just even in its simplest form, to get any closed form solutions out of. That's partly why that's an important model. The other thing is that this type of system occurs very frequently. You see it all over the place. It's like, well, once you're aware of it, all of a sudden you're noticing this everywhere. At least I am. Your mileage may vary, as they say. So, and then we said, well, let's look at our model and look at the system we're modeling and see whether or not they really coincide. And for a particular system, we noticed that, or at least hypothetically, that there was only a finite amount of waiting room, and that any arriving customer who found all the waiting room full would basically leave. That was like a lost customer. So that was again, that's an example of an iterative modeling where we start simple, and then this is something that I advocate. Start with the simplest possible model that does kind of something, and then look at it and see, well, where does it fall short? Remembering that all models are going to fall short in some way or another, but some fall short egregiously. The egregiousness of the finite capacity situation is that because the multiple server queue in its basic glory does not have that constraint. And we notice that customers in our system sometimes show up, and if it's full, then they leave. Okay, time to talk through. Yeah, sure. Okay, so that's an example of a situation where the model and the system we're modeling were at odds. Now, you probably haven't been on campus yet, but on campus, there's an outdoor little place where people go and get lunch. And around lunchtime, it's outdoors, so the line can be as long as you want. There's no built-in capacity. So for a situation like that, the multiple server queue would at least be okay in terms of assuming that infinite capacity. So there's a situation where it is a good assumption. So sometimes it's finite, sometimes the infinite is a reasonable assumption. So today we're going to look at another difference between our basic multiple server queue and and the system we're modeling. And that's tandem queues. So what we notice in the system we're modeling, again, this is somewhat hypothetical, but this is something that comes up, is that you know what tandem means. A tandem bike is where you have two of them. A tandem queue is where you leave one queue and you wait on another queue. So you hurry up and wait, and then it's only when you finished in the second queue that you're done with the system. I recently did the vaccine thing over at DLI, and we went in. There was there was a check-in place, and then when we went there was another place that took the paperwork and then did something, and then we went to another place where we waited to actually get the shot, and then we went to another place where we just kind of waited for them to finish processing, and then we were finally done. So that was just a situation where there were basically 3 or 4 of these stations. So we're going to start with 2, and there are 3 variants of this. The simplest is that there's essentially 0 time between the stations. Another one is where there's a non-zero time between station, and then there's a third option that we encounter where we only go to the second station with a certain probability. And we'll see what that looks like as we get to it. All right, so the basic tandem queue, and we'll start with 2. As I said, in the vaccine thing that I described, there were like 3 or 4 different stations if we were modeling it. But we're going to start with 2. So customers receive service from a first multiple server queue. Okay, so we come in and that's the one. You might think of something like the DMV is another example, where you kind of go, you check in, and you wait until you're called, and then you're called, and then they give you the test, and then when you're finished with the test, you go and wait on another line. They take your picture eventually and stuff like that. And I'm sure you've seen and encountered systems like that. Okay, but we're just sort of starting with 2. So when we finish service with 1, we get service from a second. So and it's here's kind of a picture of that. So what we have is, so here's where the customers here are coming in from the outside. And then here's our first station. In this particular one, we have 5 servers here. Again, they wait on a single line and then go to the respective servers. Then when they finish with that, then they don't escape the system, but they simply wait on a second station. In this particular system, the second station has 3 servers. So you immediately see that there, in terms of parameters, we now don't have 1 parameter for the total number of servers. There are a total of 8 servers altogether, but that's not an effective state variable. We really need to break them out until the 5 here and the 3 here in this particular case. We're not going to build a model, though, that is hard-coded to have 5 and 3. This is just by way of example and to understand how the system is going to work. Okay, so given that, we need to define our parameters. So first, the customers coming in. We have 1 source of outside customers. That is, in this system, the customers aren't allowed to sneak in from here. Okay, so as before, we're going to model that just with these inter-arrival times. Now, the thing is that we have a first station and a second station. So our basic multiple server queue, we had the number of servers and the service times, but now those have to be 2 different things. In other words, to capture this, here we have K0, and we're using this silly zero-based indexing. Why? Because when we get to putting it on the computer, that's how it's going to be looking. So here there are 5 and 3, and that just to emphasize that there could be a different number of servers at each station. So we want to we explicitly capture that with our parameters. And the second thing is the service time. So the service times for this first part have nothing to do with the service times at the second station. In other words, the task that these servers are doing is going to take a certain amount of time. And again, we're going to typically model that as a random variable, that as we've already seen with the arrival process on the computer, and at least theoretically with the multiple server queue. And likewise, the second station is going to have a completely different distribution. So we don't want to say that they're going to be the same, because that's not going to be a realistic way to model it. And the way to, how would we figure this out? Well, again, we would, if we were trying to configure this system and figure out what that is, we would observe this system, observe this first station, and figure out what distribution is a reasonable fit for this. And then we'd observe the second station and see what distribution is a reasonable fit for that. The chances are that they're going to be different. They could be completely different distributions. They have completely different parameters, okay? So these are the 5 parameters for our model for our tandem queue.
So there's not an inner arrival time for the second station, not station, by second station.
Yeah, great point. So if there were, that would mean that people are sneaking in from the side, and we don't allow that. Okay, so that's not something that we do. So this is an important modeling concept to have here. In this case, the only outside arrivals are here to the first station. There is no inter-arrival time to the second station. It is purely dictated by the completion of service at the first station. Okay, that's an important thing to get. Okay, so we're not just sort of copying and pasting the entire model, because the entire model would have 2 inter-arrival times.
So the inter-arrival, so the completion of service for the first station is equivalent to the second station inter-arrival time.
I strongly encourage you not to think of it that way.
Okay, all right.
The inter-arrival time is a way of modeling these arrivals. Now, yes, there is a time between arrivals here, but that's not something that we can specify beforehand. See, as a parameter, this inter-arrival time outside for customers outside the system is something that we can capture. We can know beforehand. The quote inter-arrival time here is dependent on how this first queue, this first set of servers operates. And that's not something that we can easily capture with a single distribution, a priori at least. I mean, obviously, because the way that the process that produces these arrivals to the second station involves this first station. And so that's not something we can write down as a parameter. That's something that happens with the model. Okay, so the model is going to produce that. Okay. So now in terms of states, again, we need 4 state variables now, not just 2. Because, and I can see, oops, come on. Okay, and forgot to do this. This is very important, because the initial number of servers at the first station is the total number of servers, and likewise at the second station. Okay, so we need to have like 1 variable for the number in the queue does not completely capture it. So if we look at this, at this point, there are 3 in the first queue and 2 in the second queue. There's a total of 5. But if I say that there are only 5 in the queue, then you don't know if it's 3 and 2 or 2 and 3 or 5 and 0 or 4 and 1 or whatever. But if I say Q0, in this case, Q0 is 3, and here Q1 is 2, then that completely captures what the state of the system is as it is here. So I need all 4 of them. Okay, so now the next thing to do, and I'm going to now move to my doppelganger, was going to share a whiteboard, because this is more like what I'm going to be asking you to do in a comparable situation. Okay, remember that let's look at our states. We have Q0, Q1, S0, and S1. Those are our 4 states. And so one approach is, well, let's start with the run event. We always start with the run event because if we have completely defined our state variables, we can always write that down. So our run event is always going to initialize our state variable. So Q0 is 0, Q1 is 0, S1, S0 is K0, and S1 is K1. And I like to put little curly braces around these. You don't have to. The important thing is to get these, oops. To get these values here. Okay, so now the next step is to say, pick a state variable and say what could change that state variable. Well, one thing is that we have an arrival of a customer from the outside, and that would increase it by 1. And that's an arrival to the first station. So I'm going to call that arrival 0. And again, that 0 is not an argument or a parameter or anything. It's just part of the name. Okay, that's one way that it can change. What's another way that it can change? Well, it can go down by 1 when somebody moves from the queue into service. And that we were calling start service. But since, and again, I'm going to put a 0 on there. Again, that's part of the name. That's not an argument. In a few classes, maybe even the next class, we're going to look at arguments on events. That is a thing. But for right now, the start service event decreases the queue at the first station by 1. Okay. Now for Q0, the number in the queue at the first station, those are the only things that can change that value. So since we're kind of working with the first station, let's look at S0. So S0, what could change it? Well, we could lose 1 when we start service. At the first station. So when the start service event at the first station, that is station 0, decreases Q0 by 1 and decreases S0 by 1. Okay, what else can change S0? What we've been calling end service. And again, what you call them is not important. That is, that name doesn't mean anything other than to give an indication of what the thing is doing. In other words, you want to name your events in a way that kind of represents what they're doing, but the name itself doesn't do anything. Okay, so that takes care of, so basically Q0 and S0, those are the only two possibilities. Now let's look at Q1. Okay, what could change its value? Well, when a customer arrives to the second station, let's call that arrival 1. Again, the 1 is just part of the name. Again, so sometimes you'll see like a plus equal, just because when I type, I can sometimes lazy. Okay, the other thing that can change Q1, the number in the queue at the second station, is that they start service at 1. And again, we're calling it start service, meaning, but that's because that's a name that roughly describes what's going on. Okay, so now we've completely specified Q1. Now let's look at S1. Well, at the same start service, we could lose a guy. And then finally, we could get him back at the end service. And those are the only possible state changes for S1. Now, there's no law that says that we're done. There's no law of nature. There's no law of event graphs or discrete event that says that we're done. We're done when we're done. We're done when there's no more, there are no more options. Okay, so in this case, we do happen to be done, but we're not done just because we've made 2 state changes. That's not the thing. The thing is, we're done when we've made all of the possible state changes. And it may be that that a given state variable may change its value at more than 2 events, maybe 3 or 4 or 5, it may be just 1. Okay. So I'm going to move back to where are we here? Okay, so we've done the states. And so basically, this should be roughly what we've arrived at. And then notice that again, I was sort of lazy here. So I did the plus equal and minus equal. Again, it's exactly the same thing, just a little bit less typing. Okay, so this is how I strongly encourage you to when you are doing this, and as you've noticed, I'm starting to ask you to do it, but when you're doing it, just be very, I encourage you to not be impatient to start drawing the edges. In other words, make sure that you have all of the state transitions before you go on with the edges. And in this particular case, what we have is at the top part. Okay, so if we were to only look at things from here on up, this is structurally identical to the multiple server queue. And if we only look at the bottom piece, we see that that's almost equal, that's almost the same as a multiple server queue, except with the variable, with the state variable Q1 and S1 instead of just Q and S. Okay, so here's the difference. The difference is the arrivals come here. You were asking about, is there an inter-arrival time to the second one? And that would, if there were, then you would have something like this, but we don't. You don't want that. This is not what goes on. What goes on is, okay, so we see this piece, we've already, from here, we would, like if I were drawing this, we could draw it like this. Okay, so these are the arrivals. Then an arrival would schedule a start service if S0 is bigger than 0. Again, this is how you would want to do this. The start service schedules an end service with a TS0 delay. The end service then would schedule a start service at the same station if there was somebody waiting. And then if we look at the bottom piece, then we have something very similar. So an arrival at station 1 would schedule a start service at station 1 if there was a server available. The delay is based on the service time at the second station. And when we finish, we can serve another customer in the second station if there's somebody waiting. Okay, this is an important piece here, the thing to understand. Okay, so now,
Sir, that I get a little confused on one part. I think I know the answer though. On the arrival, the A that comes back to it, that just means schedule another arrival.
yes. Yeah, this is the scheduling. There should be a T sub A. Yes, the scheduling edge says when one event occurs, it schedules another event possibly with a delay. If it points to itself, then that means it schedules another one of itself. Okay, so you have that exactly right. All right, so now here's the thing. If we look at this event graph here, what will happen? Well, since you've done it by hand, you can just sort of envision what would happen. You'd have the run event, it would schedule the first arrival. The first arrival would schedule a start service, and then more arrivals would sort of be coming in, depending on how many servers we had, it would be carrying on. And at some point, an end service is going to occur. Now, these event graphs are just as stupid as a computer program in that they do what you've told them to and not what you want them to. So how does this system work? The way the system works is that when we finish service at one station, we arrive to the next station. That is not captured by our model yet. What does that mean in the model? That means that when an end service occurs, that schedules a start service. Well, it schedules start service here, but it also schedules an arrival to the second queue. And we model that with a scheduling edge. And in this case, we're modeling the time between the stations is effectively 0. Again, obviously, it's never literally 0. But the idea here is that the time that it takes to move from one station to the next is negligible compared to the other times in the system. So, for example, when I was checking in for my vaccine, it was at one desk, and then I just had to walk into the next room, and it took maybe all of 10 seconds, as opposed to a couple minutes at the check-in. Actually, at the check-in, I'd forgotten to bring my paperwork, so I had to fill out a paper. I had to fill it out, and so I was there for about 5 minutes, as opposed to 10 seconds. So it's not the worst thing in the world to model, to at least start with a modeling of that time between them as being very small. However, supposing we were modeling, supposing the first station was the security check-in at an airport, and the second station was checking in at our gate. In that case, there's a non-trivial amount of time that it takes to get from security to the gate. At least every time I fly, it seems like I'm always at the farthest gate in the whole airport. So that's part of Murphy's Law, I suppose. So, and that's something that we can sort of take a look at. Okay, so here, basically here, that's this scheduling edge right here. It takes the end service event schedules an arrival. And the one thing that I want to emphasize again, this looks superficially like other network diagrams that you may see. For one thing, and I think somebody mentioned this, it may look kind of like a finite state diagram, but it's, if you know what a finite state diagram is, I hope you can see the difference. In a finite state diagram, the nodes are actually the states. Here, the nodes are the state transitions. There's a big difference. And if you think about it, for a model like this, cannot be represented as a finite state machine. Why? Because of the state variables Q. what is the upper limit in this model? What is the upper limit on the value of Q? Anybody? How big could Q get in principle?
I
There-
mean, it's
Infinite?
infinite.
Yeah, there's effectively no limit. You know, we have not put a limit on it. So how can you represent a state that has infinitely many values with a finite state machine? Can't be done. I mean, a finite state machine by definition has finitely many states, and this has infinitely many states. So you know, when you're doing a finite state machine, take everything you know about event graphs and put it aside. If you're doing event graphs, take everything you know about finite state machines and put that aside, because they're entirely different models. You know, finite state machines are great for what they do. In this situation, it's just not what we're talking about here. The other thing to try to take out of your mindset is this kind of also looks like a flow diagram. So and there's a good reason for that. You might think, okay, somebody arrives here and then they go here and then they go here and they go here and they go here and they go here. There's kind of a sense in which that's true, but that's also not the best way to think about that. A better way to think about it is like we're looking down at this system, and we could conceptually think of these events maybe flashing as they occur, and they flash in seemingly random patterns. In other words, in a flow diagram, you go from here to here to here to here to here to here, but that's not how these events are going to work. As you've seen with doing it by hand, the order that these events occur has almost nothing to do with the order that they are listed here. So, you know, if you ever kind of think of the words like, okay, guy, we go here, that's kind of the key phrase to take a step back from, because we don't go anywhere. These edges mean that this event schedules this event. It doesn't go anywhere. It just simply puts it on the event list. That's it. Okay, so now let's look at, we look at our system, and basically, one of the first ones is something like the airport situation that I described. The time between if I'm modeling as a tandem queue, the security, you know, the TSA and the gate, the time it takes to get from the TSA to the gate is a significant quantity. Obviously, if I'm modeling an airport, then there are a whole bunch of other, even if I'm modeling it at a very simple level, you know, what is that travel time? Well, it actually depends on where the gate is relative to the security check-in. Otherwise, you know, it might be, and I don't know if you've ever had situations like this, you know, sometimes there are systems where I check in at like one building and then I have to go to another building to do the next stage. And again, if that's the case, then it's going to take a non-trivial amount of time to move from the first to the second. So my model here assumes I can get there in 0 time. And if that 0 time is not a good assumption, then I better do something else. So what I need to do is add a travel time. I'll call it T sub T as an additional parameter. That's the time it takes to travel between the first and the second station. And so what do? Well, I can take my model and I can simply add that time as a delay between my end service and my arrival. And now I've captured that. I've captured that in the situation where I can represent this as just one variable easily. As I said, in the case of the airport, depending on how detail I wanted to get, I might want to get that travel time could be significantly different depending on how far the gate actually is. And if I'm modeling passengers who are, the people in the queue at TSA are going to all sorts of different gates. And so having just one random variable for that may be insufficient. But certainly modeling it as a random variable, let's say I'm only looking at so let's say I have a very small airport that only has like one gate, but it's located a fair distance away. Okay, so then having one travel time would be a reasonable thing. And having it be different values is also another reasonable thing because people walk at different speeds. And so if I were observing the system, I would notice that even for customers going from security to the same gate, I would get different times that it would take them. Okay, some are very fast, some are very slow, a lot are in between. Okay, so the key thing here, again, this iterative modeling, we look at our model, we look at this model, and then we look at our system and say, is this realistic? Is this a realistic assumption to assume that there's no travel time? And in this case, if in the case that it is not a reasonable assumption, we simply add that delay. And it's, if you notice, it's just a simple tweak. We define one more parameter and then add it to a scheduling edge that we already have. And that's the advantage of an iterative modeling process, is that is given that we have this model, it's an easy tweak to add this time. Now here's another use case for this type of thing. Sometimes the first station might be that we're processing a part. And then as part of that processing, we kind of examine how it was done. And in this particular one, we're going to assume that no parts are actually lost, but some parts are not exactly correct. And if they're not correct, they're going to have to go for rework. So our second station is going to be only for those parts that need rework. Okay, and that's in many facilities, that's actually a separate thing. The rework is a separate thing. In some it might be at the same station, but in many it's the rework is somewhere else. Okay, so how do we model that? The simplest possible model of that is to say, well, what's the probability that it'll need rework? Where can we get that number? We can probably get that by just sort of counting over a period of time, like what proportion of the parts that we process actually do need rework. So we're going to have a probability P that's going to say this proportion of parts are going to actually need work. So how do we model that? Well, we have a parameter P, and then we define a sequence of uniform of remember what IID stands for, independent, identically distributed, uniform random variables. And now our edge condition is U less than P, because if we have uniform 0, 1 random variables, this will happen with probability P. So how do we do that? Okay, so we define our two parameters. One is the probability of requiring the second station, that is the rework. And then the second is this uniform, a sequence of uniform random variables. And then we simply add this Boolean condition. Remember that the Boolean condition is what says, in this case, an end service will schedule an arrival only with a certain probability. Okay, so in other words, this, when an end service event occurs, this scheduling edge we basically flip a coin, a weighted coin with probability P of coming up heads. If it comes up heads, then there's something wrong with the part. We need to rework it. The second station does the rework. But if it comes up okay, then we're just done. Okay, so we've seen 3 extensions to our model. Okay, one is just the simple tandem queue where instead of just having one server, we go to a second. And then we saw 2 variants of that. One is where we added the travel times, and then a second where we added this idea of that not everybody goes to that second station. It's only with a certain probability.